Howdy friends, here we are snowed in again, so I figured that we could talk about substitution with definite integrals. Let's review the substitution process first. We're going to look at two examples, one that's fairly easy and another that's more complicated. Consider the integral of x e to the x squared dx. We walk through our integration process. Do we have an exact match for our derivative rules? No. Can we do some algebra to simplify this? No. And so we consider substitution. The most obvious candidate for substitution is to let u equal x squared. And so we compute du equals 2x dx. Well, that's good news because the x dx is present in the integral. The only thing missing is the constant 2. And so we solve for x dx, giving us 1/2 du, and we replace everything in the integral in terms of u, giving us a very simple antiderivative, which evaluates to 1/2 e to the u plus c. We then back substitute to give ourselves 1/2 e to the x squared plus c. But we're not done. We're not done until we check. And so we check by taking a derivative of our result and see that yes, indeed, the derivative of 1/2 e to the x squared is 1/2 e to the x squared times the derivative of the inside, which gives us x e to the x squared, and it checks. We're very happy with this process, and we observe that it worked because we took our integral in terms of x and replaced everything in sight in terms of u. And in fact, that is our substitution slogan: replace everything in terms of u. Now let's consider a more complicated example: the integral of x times the square root of quantity 2x minus 1 dx. And so we walk through our process again. Is this an exact match for a derivative rule? No. Can I do any algebra with this? Tempting, but I don't have any exponent rules that apply to the square roots of differences. So there's nothing really that I can do here with algebra. And so that leaves us with substitution. The obvious choice for substitution is u equals 2x minus 1. And so we compute du equals 2 dx, and dx is therefore 1/2 of du. So now we begin to substitute. It's easy enough to see what happens to the square root of 2x minus 1, and also to the dx. We can replace those with u to the 1/2 and 1/2 du, respectively. But what happens to the x? For that, we need to go back to our u and solve for x. And when we do, we find out that x equals u plus 1 over 2. That allows us to replace x with what it is. X is u plus 1 over 2. And so our finished integral looks like this: the antiderivative of u plus 1 over 2 times u to the 1/2 times 1/2 du. Honestly, this integral looks pretty ugly, but then we begin to use some algebra, and we discover that we can pull out 2 factors of 1/2 with the constant multiple rule, and then we can distribute the u to the 1/2 to each term in u plus 1. And that leaves us with an integral that's not so bad: 1/4 the integral of u to the 3/2 plus u to the 1/2 du. We can integrate that term at a time, adding 1 to the power and dividing by the new power, to give us 1/4 times the quantity 2/5 u to the 5/2 plus 2/3 u to the 3/2, plus, of course, the obligatory constant c. If we distribute the 1/4 to each term and back substitute 2x minus 1 equals u, then we get the final result: 1/10 of 2x minus 1 to the 5/2 plus 1/6 of 2x minus 1 to the 3/2 plus c. But we are not done until we check. And so we take the derivative of our result, and when we do, using the usual power rule and chain rule, we end up with this result: 1/2 of 2x minus 1 to the 3/2 plus 1/2 times quantity 2x minus 1 to the 1/2. Well, this presents us with a puzzle, because it does not exactly look like the integrand that we had before which was x square root of 2x minus 1. So did we fail in some way? Before we declare failure, which would require us to go back and find our mistake, let's actually check and see whether or not we really did by graphing our result compared to the original integrand. Lo and behold, when we graph our result compared with the original integrand, they're the exact same function. Lo and behold, we appear to have gotten the correct answer, but it's not at all obvious how. Let's take a closer look. What we observe about our checked result is that it has a common factor of 1/2. It also has a common factor of 2x minus 1 to the 1/2 power. So, if we factor out both of those common factors, we are left with 1/2 2x times the quantity 2x minus 1 to the 1/2 times 2x minus 1 to the first power, that is the 2/2 power, plus 1. Well, when we simplify that, the 2x minus 1 to the first plus 1 collapses to 2x, and 1/2 times 2x is x, so that our result is algebraically identical to the original integrand. The moral of the story here is that sometimes you have to be patient with your checking. Now for something new. We'd like to consider how substitution works when we have a definite integral. Consider this integral, the integral from 0 to 2 of x e to the x squared dx. The substitution process is going to be exactly the same. We're going to let u equal x squared as we did before, so that du is still 2x dx, and x dx is 1/2 du. So we replace everything in sight in terms of u. But what about our limits of integration? The limits of integration were originally x values. We were integrating from x equals 0 to x equals 2. So if we are going to replace everything in sight in terms of u, we must find the corresponding u values. But that's easy to do. We can compute them from what u is. If we simply substitute x equals 0 into the expression for u, we find that u is equal to 0 also. Likewise, when x is equal to 2, u is equal to 4. And so this gives us the new limits of integration in terms of u. Our new integral is the integral from 0 to 4 of e to the u 1/2 du. Now we get a lovely bonus. Because this integral is exactly equal to the original, I can evaluate it directly without having to back substitute. The integral of e to the u 1/2 du is simply 1/2 e to the u from 0 to 4. And that gives us the answer, which is 1/2 times the quantity e to the 4th minus 1. Well, so how do we check our work? Honestly, when I have to check definite integrals, I prefer to evaluate them on the calculator directly if possible. And when we do, we find that we get an answer that agrees with our result, which is 26.7991. I'd like to say a little bit more about why we did not have to back substitute. When we performed our substitution by substituting everything in terms of u, including the limits of integration, we transformed the region e to the x squared from 0 to 2 into a different region, 1/2 e to the u from 0 to 4. Those two regions have a different shape, but because we were scrupulous about replacing everything in terms of u, they are guaranteed to have the same area. So, it is not necessary for us to back substitute. We can simply evaluate the new integral, and it is guaranteed to have the same area as the old, the same value as the old. So this is a good opportunity to remember our slogan for substitution. Replace everything in terms of u, including the limits of integration. Now let's consider a more complicated example, the integral from 1 to 5 of x times the square root quantity 2x minus 1. Just as we did before, we let u equal 2x minus 1, so that du equals 2 dx, and dx equals 1/2 du. And also, just as we did before, we solve for x equals u plus 1 over 2, so that we can replace everything in sight in terms of u. What about the limits of integration? Well, yes, we compute those too. U of 1 is equal to 1, and u of 5 is equal to 9. And so we replace everything, getting the final integral from 1 to 9 of u plus 1 over 2 times u to the 1/2 times 1/2 du. And just as we did before, we use the constant multiple rule to pull the two factors of 1/2 to the outside. And we can now integrate directly, term at a time, giving us 1/4 times the quantity 2/5 u to the 5/2 plus 2/3 u to the 3/2 from 1 to 9. Directly substituting in the limits of integration gives us this fairly awful expression that I will not pronounce. And if you plug it into your calculator, you will find that it has the value 28.53333. The way that we check our work is to evaluate the original integral on calculator. And when we do, we find that it has the same exact value, and we declare victory and retire the field. What was particularly nice about this example is that we did not have to back substitute. Furthermore, because it was a definite integral, we could check our work by calculator directly. Now, you may think, that's cheating. Why would I evaluate the definite integral by hand if I could evaluate it on the calculator? And that's a fair question. Keep in mind that a large part of this is confirming what we believe to be true. We're checking our methods. If we were in the wild and we had no calculator, then we would have to actually confirm by back substituting and evaluating. To sum up everything that we've learned, it really comes down to our slogan. When we are substituting, we replace everything in terms of u, including the limits of integration. Have a great day.